Let's talk about energy transfer in waves. In order to understand waves, we must understand the properties of waves. These include wavelength, amplitude, and frequency. You may have seen waves on the surface of a sea or an ocean. These waves have high and low points. The distance between one high point and the next one is called wavelength. If the wavelength is small, the waves are closer together. Take a look at the video on the right. The wavelength is shown in red. That's the distance between the high point of one wave and the high point of another wave. Waves have high and low points. Big waves have a lot of power and strength. The height or strength of a wave is called its amplitude. It is the distance from the wave's rest position to its high point or low point. Take a look at the video on the right. The amplitude is shown in red. That's the distance between the rest position and the highest point of the wave. Frequency is the number of cycles a wave completes in a period of time, or the number of times something happens in a period of time. So if we look at the 3 centimeter mark, every time a wave passes this point, we can count that as frequency. Now let's put what we've learned together. In this video, you'll see a high frequency and high amplitude wave. As you watch, I want you to pay close attention to the wavelength. What happens as we increase the frequency and the amplitude of the waves? This time we're going to look at a low frequency and high amplitude wave. As you watch, look at what happens to the wavelength each time. By decreasing the frequency, we've changed the wavelength when we compare it to the high frequency, high amplitude waves. What are the differences between this wave and the last set of waves? Finally, we'll look at a high frequency and low amplitude wave. Again, pay close attention to the wavelength as we watch. You may notice a difference between this wave that has a high frequency and low amplitude and the wave from the last set that had a low frequency and high amplitude. What happened to the wavelength? Now that you've learned about wavelength, amplitude, and frequency, try this investigation at home. We'll show you what this looks like in the next part of the video. You'll need a large plastic food container. If you can find a clear one, that will be better. Use 2 or 3 different sized rocks or marbles. You'll need a ruler and paper towels. Let's look at the waves investigation in a different format. In this demonstration, the water drops will represent the rocks. Pay close attention as the drop hits the water to the amplitude of the waves. This represents a small rock. What do you notice about the size and the amplitude of the waves? This demonstration again shows a small rock, but from the side view. You'll be able to see the waves from the side, and you'll be able to see a graph to show the size of the waves as it ripples through the water. What do you notice about the amplitude of the waves? Let's try the same investigation with a medium-sized drop that represents a medium-sized rock. Pay close attention to the waves that are created and the amplitude of the waves. This is the same investigation using a medium-sized drop that represents a medium-sized rock. This time we'll look at it from the side view. Pay close attention to the amplitude of the waves. Finally, let's look at a large drop that will represent the large rock hitting the water. Pay close attention to the amplitude of the waves. This is the side view of the large rock hitting the water. Pay close attention to the amplitude of the waves. There are other types of waves besides water waves. Let's explore a little bit more about sound waves and how humans hear sounds.
The performance group Stomp celebrates rhythm. When the cast pounds on garbage cans or bangs their poles on the ground, they transfer the energy of their movements into energy that we hear as sound. Sound begins as vibrations that get carried to us as waves traveling through the air. The vibrating air spreads out through the theater and sets off a chain reaction in the ear. Our outer ear helps us locate sound. The shape of it might seem kind of odd, but it funnels sound waves inside. These sound waves usually hit one ear before the other, and this helps us determine where sounds originate. From the outer ear, the waves travel inside, where they strike the eardrum and rattle three little bones. The hammer, anvil, and stirrup are the smallest bones in our body. As they vibrate, they carry movement to the snail-shaped cochlea. About the size of a pea, the cochlea contains fluid that moves thousands of cells with special hairs. Rows of hair cells pick up vibrations and change them into electrical signals that get sent to the brain. These fragile cells are all that stand between us and silence. Over time, continuous exposure to loud sounds causes them to stiffen and die. Our ability to hear is more complex than we think. Usually, we hear dozens of sounds at once. Yet we're able to process them all and pay attention to sounds most important to us. Have you ever thought about lunch in a noisy room? This man is talking to his friend and listening to what she has to say. At the same time, he hears someone laughing, sounds of other voices, music in the background, traffic outside, dishes clanking, chairs moving. He's bombarded with sounds that his brain is able to filter. Our ability to handle so much information is extraordinary. We do more than simply take in sounds. We recognize them and often respond to them emotionally. Our brain has evolved to recognize the patterns and rhythms from all sorts of sounds. In fact, we make our own sounds and rhythms all the time.
I don't think there will ever be a day again in my life where I don't walk around and find rhythm in walking and breathing. And I mean, that's what it's all about.
You have a rhythm, and it's your heart. So even if you clap to just, zone into it, it's your rhythm, and it's there.
Animals use sound waves too, but in very different ways than humans do. Let's take a look and see how animals use sound waves to hear and communicate.
The animal kingdom is full of sounds that people don't hear, sounds that are inaudible to humans. In fact, most animals make and hear a broader range of sounds than we do. While studying elephants in the wild, Dr. Joyce Poole became convinced there was more going on than was meeting her ears.
For many years, we've noticed on occasion a female will suddenly freeze and all the rest of the elephants stop at the same time, as if they've heard a sound and we didn't hear anything. Or occasions where, again, a female at the back of the line might open her mouth very loudly as if she was rumbling, and yet we couldn't hear anything. And it really made us wonder whether, in fact, the elephants were making sounds that we couldn't hear.
Zoologist Katie Payne helped solve that mystery. While standing by an elephant cage, she felt a movement in the air that she thought might be associated with sound. With equipment capable of recording low-pitched sounds, or infrasounds, that we can't hear, she proved her point. By playing back the tape at 10 times its regular speed, she was finally able to hear what she was missing.
Nobody had listened for infrasound among land animals before. No one had thought there was an animal large enough to make powerful low-frequency sounds like this. And what it meant for the elephants was that they might be able to use it to communicate over long distances, because infrasound travels much better than high-frequency sounds.
Sound that falls within the range of human hearing doesn't travel very far. It consists of short sound waves that scatter when they hit obstacles. But infrasounds are made up of long sound waves that bend around obstacles with very little scattering. As a result, they travel much further. At the other end of the spectrum, bats send and receive high-frequency sounds that humans can't hear. This bat detector lowers the frequency, so the sounds become audible. Jim Simmons studies bats that use these sounds to see.
Each time the bat makes one of these sounds, it moves the ears in this back and forth pattern, scanning.
He records the bats as they use a process called echolocation to navigate through wires and catch food in the dark. With a series of clicks and calls, they send out sound waves that bounce off objects and create echoes. The echoes help them determine the size and distance of every object in their path. What remains a mystery is how bats process sound waves so quickly. They send and receive sounds as high as 100,000 cycles per second. but their brain can only process sounds at 400 cycles per second. Simmons thinks the bats do something incredible. They manage to slow down the incoming sound waves. In other words, they slow down time.
Our experience tells us what the bat does is impossible, and yet the bats fly around and do this all the time.
The last type of waves that we're going to talk about are light waves. Light waves have the same properties as sound waves and water waves, but they behave pretty differently. Let's talk about some of those important differences.
Frequency is a very important property of light waves because it is one of the properties that set light waves apart from the other kinds of waves. The frequency of a light wave determines where it appears on something called the electromagnetic spectrum. Let me explain further. Light waves are a special kind of waves called electromagnetic waves. Electromagnetic waves transfer electric and magnetic energy, and those waves are part of something called the electromagnetic spectrum. That's the name for the range of electromagnetic waves in order of frequency. All electromagnetic waves travel at the same speed but have different wavelengths and frequencies. The electromagnetic spectrum is made up of radio waves, infrared rays, visible light, ultraviolet rays, X-rays, and gamma rays. As you can see, light waves fall somewhere in the middle of the spectrum. The fact that you can see light waves is very important. That's one way they are different from all the other electromagnetic waves. They are visible. Before we go any further, let's take a moment to review what you have learned so far. You know that light is actually a visible form of energy, and that light travels in waves called transverse waves. Those waves have special properties that include wavelength, amplitude, and frequency. You also learn that light waves don't require a medium in order to travel, and you learn that light is part of the electromagnetic spectrum.
We've been talking about energy transfer in waves in the forms of water, light, and sound waves. Over the past 3 weeks, we've talked about electrical circuits and the different forms of energy as well. As you continue about your everyday life, playing games at home, going for walks, spending time with your family, playing games, and doing your schoolwork, be sure to keep a lookout for these 3 topics. You'll be really surprised how often each one of those topics has an important role in your everyday life.